So 10 to 2 is going to take us into some very new concepts. So just like when we're learning any other new concept, you might need some review, might need some patience with this. Logarithms are essentially going to become a new operation, and it's going to really hinge on a couple of key formulas, and then we're going to learn our operations that we can do, our formulas, a lot like exponents. Exponents and logs are related, that we can do to logarithms to manipulate them. Logarithms are the tool we are going to use to solve problems that have variables in the exponent position. So, why is a logarithmic scale used to measure sound? So this is one application. Many scientific measurements have such an enormous range of possible values that it makes sense to write them as powers of 10 and simply keep track of their exponents. So it's kind of a shorthand notation. For example, the loudness of sound is measured in units called decibels. The graph shows the relative intensities and decibel measures of common sounds. So the relative intensity of a pin drop is 10 to the 0, barely registers. Normal conversation is 10 to the 6th, noisy kitchen 10 to the 10th, a jet engine 10 to the 12th. If you were trying to actually write those numbers out, they would be huge. So we use the exponents, which is logs, to use a shorthand notation. And for decibels, specifically, they multiply it by 10. So you see this 12 here becomes 120 decibels. But in general, a log is the exponent needed to raise a base to a given number. Okay, definition. The exponent needed to raise a base to a given answer. So you can see right away from the definition how exponents and logs are related. So let's go over to this exponential form first. Now, this is obviously our answer, b is our base, and a is our exponent. That's how we're used to looking at things. If we take those same variables, you see that here is your base, log base b of x is equal to a. And that's how we say it. Log base b of x is equal to a, where the base of the log, that b, is the base of what we had over here. X is the answer, and what our log equals is the exponent. So being able to move back and forth between those two equations is critical. I would probably make sure that is on my cheat sheet. Now, keys. B always has to be greater than 0, which means no negatives. It can't be 1. And x, our answer, must be greater than 0. No negatives there either. So that's the rule. So those are our restrictions and our rule. So we're going to write these in exponential form. Now remember, this is my base, this is my answer, and this is my exponent. So really, remember when we have our formula of b to the a is equal to x, is the same thing as the log base b of x equal to a. All right, so we've got our base, which is g, to our exponent 2, oops, that's an 8. 8 to the 2 is equal to 64. And that is a true statement. At this point, we're not doing any math. We're just manipulating the exponent to the logarithm form and back and forth. So here we go. 16 is your base. 4 is going to be your answer. 1/2 is your exponent. So as an exponent, I have 16 to the 1/2 power equals 4. That's true because remember the 1/2 power is the same as the square root, because we can do that fractional exponent rule. So here our base is q to the t power is 7. Here our base is x plus 2 to the st power would be equal to a squared plus b squared. Now, being able to manipulate these into different formats is what's going to allow us to potentially solve different types of problems. So let's go the other way. Now let's look at our formula again. We have log base b of x equals a, and that's going to be exactly the same as saying b to the a is equal to x. So in this case, here's my base, here's my exponent, this is my answer. So where does everything go? Well, I've got log base 27 of my answer is the exponent, 1/3. If you want to go ahead and write b to the a equals x, then b is 10, x is 100, a is 2. Here, b to the a equals x, so I have log base x of 12 equals a. And even though this looks more complicated, just remember that what each piece is. So I'm going to have log to the base a plus b of 84x plus y equals 7x. It may look like nonsense right now, but we're just practicing moving between the two different formulas and different forms, because depending on where our variable is, each form is going to provide us different opportunities and options for solving for the missing variable. So let's evaluate. So really what we're asking is, what does this equal in each of these cases? Now we're most comfortable with exponents. So we are going to take these, and again, we're going to look at our formula and how we can turn these logs back into exponents. So this is our base, this is our answer, and this is our exponent. So we're thinking about 10 to what power equals 1,000. Well, if we use yesterday's concept, 10 to what power is equal to 10 to the third, well, we know, like bases, that our powers are equal. In this one, if I think about 2 to what power would equal 8, I could rewrite 8 to what power would equal 2 to the third power. So I know my missing variable is 3, because I use the rule from 10.1, like bases equal exponents. So here, 9 to what power equals 3? Well, if I think about the fact it has to get smaller, I'm thinking about the fact that it's probably fractions, and if I use my common sense, I know that the square root of 9 is 3, and so that means my missing exponent is 1/2, because remember that the square root of 9 is the same as 9 to the 1/2 power. Now log x, or log 8 of -5, if you remember from our restrictions, x must be greater than 0, therefore no solution here. You can't do it because x is a negative number. Now in this last example, 8 to what power equals 1, if you go back to your exponent rules and remember anything to the 0 power is 1, then we know our missing exponent is 0. So if we're going to continue to evaluate these, there's kind of a trick. Inverse property. Now remember, inverses are our undoing operations, our opposite operations. So addition and subtraction are inverses. Multiplication and division are inverses. They undo each other. Exponents and logs are opposite operations. They undo each other. So if you see base 6 of 6, those are going to undo each other, and your answer is going to be the exponent. Here you have 3 raised to the log base 3 power. Those two will undo each other, and your answer will be 4x minus 1. It really is that simple. It would be like, for example, if you take 1/4 times 4 times 3, these two undo each other, so your answer is 3. So in a sense, they cancel, they become 1, or they undo. You multiply by 4, then divide by -4. So if we look at another example, if you think about 7 raised to the log base 7 of x squared minus 1, that will equal, these guys cancel, x squared minus 1. But notice it's the exponent raised to the same base, so this and this, or it's the log of, we'll say m this time, of m. So if these index numbers, bases, match, then they cancel and you're left with whatever else is the answer. So if this was x raised to the log x of a, it would equal a. If this was log m of m to the a, it would equal a. All right, those are going to cancel. So when we look at some more examples in solving situations, remember again, this is my base, this is my answer, this is my exponent. So I'm going to rewrite this as 8 to the 4/3 power equals n. Now 4/3 power is kind of difficult to deal with, so I'm going to rewrite this as 8 to the 3rd to the 4th, because I know exponent rules that x to the mn, I've multiplied, that's a power to a power. I can either do it that way, or I can raise it to the nth and then the m. I can split it, and it's going to be the same thing because multiplication, the order doesn't matter. Now, it's much simpler to me because I know that the 1/3 power, the cube root of 8, is 2 to the 4th, and so I know that n is 16. I could say, well, 8 to the 4th and then the 1/3, but that number becomes so large that I don't know how to do that in my head. You will get 16, but it's much simpler when you see the root to just go there. So this one becomes 27 to the 2/3 power equals n. In the same way, I'm going to split this as 27 to the 1/3 then squared equals n, because I recognize 27 as a perfect cube. The cube root of 27 is 3, and so that I know n is 9. Tune in to part 2 for the end of the lesson.